Good afternoon, everyone. Quang. Today I'm talk about OpenSSL, a tool that finds few bugs in this program with incorrectness logic. This was published in Oxford this year. Sean worked with Azalea, Jules, Josh, Barrett, and Peter. So my talk is around 18 minutes, and at the end, Peter may have some comment. Okay, so I talk with first Axiom of a bug catching tool. So if you are going to develop a new tool to find bugs, please don't spam the developers. That is Axiom from Peter. So our engagement with OpenSSL developers so that they are very sensitive with false positives. So our tool find 41 bugs and 15 of them are new bugs. So we report the bugs. Also, we propose the fix and in a pull request. So this is one of the bugs we report to them. So and our fix is in the plus side. In this function, first it called fmalloc at line 956. So fmalloc will allocate a new memory, access the address, the memory address to the pointer. This thought the allocation may fail. So after it reset the content to 0, and because the allocation may fail, so this one may return a null pointer error. So to prevent the bugs, we just add the null checking. When we report the bug to developer, they just say that a comment in the push request and say that that's false positive because fmalloc doesn't return if the allocation fails. So that's not only one, more than 50% of the bugs we report to them, they comment very similar like that. That's false. So we also very nervous. And first I run the tool, check the error trace. So you can see that actually fmalloc here, the tool said that the null pointer reference come from fmalloc called the OpenSSL malloc. That's the malloc in OpenSSL. And OpenSSL may return null here, the null pointer. So nothing wrong for us. So to double check, I do correct search in OpenSSL so-called, and I found that what I found is that there is another fmalloc in another file, and this one actually it doesn't return. It do null check and it doesn't return when the allocation fail. So we just report what's it. Our findings to the developer. They agree that actually the so-called has a bug, but he creates another push request to make the two f is the same, not return when allocation fail. Okay, so our tool is pull-as we develop a tool to prove the presence of bugs, and our tool doesn't spam developer very much, and it's very scale. It's scale in 3-dimensional. It can support very large team, around 1,000 of developers, and it can verify 5 bugs in million lines of code, and can support around 10,000 diff commit per week. So and especially it can support CI reasoning, so it can support the run anywhere analysis. So our tool is based on Infer. So Infer is a compositional set analysis, and it can analyze the whole Linux kernel less than 30 minutes and acquire space Facebook. But Infer has two main limitations. The first one is glasswood foundation, and the second is don't have any mechanism, any algorithms to report bugs for compositional for run anywhere. So we discussed this in detail. So glasswood foundation. So when we set a tool to find bugs, we talk about under approximation and over approximation. For example, in KLEE and CBMC, they starting from the main function, they analyze the whole program, and because they do under approximate the behavior of the program when they report a bugs, that's bugs inside the actual program behaviors. So that's it, 2 bugs. But there are some pros and cons here. The cons here, so they not scale to 3-dimensional. I just have before. And second, so they not really have a memory folder for unbounded symbolic heap. For Infer, So infer is compositional, can support run anywhere analysis, and it's very scaled. It has some memory models based on separation logic and bounded heap. But because infer is over approximate the behavior of programs, so when it report a bug, the bugs may be outside of the actual program behaviors, so it may return false positive. So we put two systems together, pros and cons, and we ask the question how to achieve both scalability and precision, not very much false positive. So to have a system scale and precise bug finding tool, so maybe we have two options. We have first option is under approximate analogy of infer. So we say that we do under approximation analysis. The second option is a compositional analogy of KLEE or CBMC. Okay, so to support the scale. And the memory model, maybe we choose an under approximate analogy of separation logic. That is some kind of incorrectness logic, separation logic, as I proposed in CAP 20. So in this work, we choose the first one. Okay, so maybe other people may choose the second one, but we choose the first one, and we choose an under approximate analogy of infer using incorrectness separation logic. So we talk a bit about our, not very much, but a bit about the technical. So compositional reasoning is about divide and conquer. So we will divide the whole programs into the small part and analyze the small part, get some analysis result, and combine them, compose them together. So for even a programs, we use a cone graph, dependency graph. Possible in this example, we have two connected components. The component is the left-hand side. We have the function f1 cone f2, f2 cone f3, and f4. And f3 is the cell recursion. So we will analyze bottom up from the leaf to the root. Okay, and the analysis result here is the summary, the IL triple, the incorrectness triple. We find that and we compose. Also, when we analyze F2, we use the IL triple of F3 and F4 to analyze F2. We not go into F3 and F4. Okay, and means here how we compose by under approximate by abduction. So we go a bit detailed. In first, what is incorrectness triple? We start with the under approximate triple. So the triple is PCQ. P is precondition, C is the programs or statement, Q is post condition. So it means that for all the state S in the post condition, so S can be reachable by running the programs C, and we achieve from some state from S prime in the precondition. So for incorrectness triple, we have one more component. That is the epsilon here. The epsilon is the exit condition. So when the program exists, it may be okay, that's normal execution, or maybe error, that's normal execution. And let's see two examples. The first example for the, that is the triple, the summary of free function. So we say that if y point to a heap allocated in the free condition at beginning, so the cell pointed by y will be invalidated, but will be deallocated when we execute the free. Okay, but in the second example, if we say that if y has been deallocated already, which we free again, so we will get an error. That's the double free error. Okay, that's the triple to summarize the normal execution and abnormal execution. So the analysis problem. So given a program, so we will build some control flow graphs here. And in this one, we assume that all the IL triple or specification of atomic procedure for the assignment or some all the libraries, the triple of libraries for the pre-event. Now we use compositional analysis to find the summary of the precondition and post-condition of the whole program. Okay. So that is the question we need to answer in this work. And what is the compositional? That's based on by abduction. So by abduction, it will involve precondition and post-condition. So we start with the over approximation by abduction first. So given assumption A in the left-hand side and C as a conclusion on the right hand side, we need to find M and F so that A star M implies J star F. Star here is the separation conjunction in separation logic, and M will go into the precondition of the programs, and F will go to the post condition of the programs. Okay, so for under approximation, we swap F and M versus F and M. Now the question is that if given a program, we can describe a specification, pre and post condition, but when we will report the bugs to the developer. Okay, so for example, in this example function F here, so F will update the content of the input to 42. So should we report the bugs there? So it's very much depend on the status, the values of the input X. If X has been allocated, so this function don't have any error. But if X equal to null, so we should report the null pointer errors there. Okay, so some existing work, for example, infer, usually they just use some heuristics because infer they prove the correctness. When they couldn't prove the correctness, so they will base on the shortcut around the failure, and they decide whether they report the bug or not. Another tool, KLEE. KLEE actually they the 1% of compositional analysis of KLEE. They just use some heuristics and human annotations, and they can find 11 real bugs in 1% of OpenSSL, but the fix rate is very low, less than 3%. For our work, we find the precondition and post condition, the typos, and in the error typo, we develop some theorem to say that whenever to classify whenever this one, the error specification, will become the real box, regardless of any code to the function. Here we have two examples. We come back to another the simple I showed beginning the talk. So here, because we say that any values of the input, this bug happen. So that means any code to this function, this bug happen. So we will classify this one as the manifest error and report it to the developer. Another example here. So you see that the malloc here, they under condition the count equal to 0, and after that we update the content of the new allocation memory here. So this means this may has a null pointer reference error there, but it's only happen when the count equal to 0. So we call that actually a latent error, and we don't report the bugs to the developer, but we keep it, we store it in the database, and maybe later for another function, possible main function, it's part the right count equal to 0 there. So this point, the bugs happen regardless of any call to the main function. So we report the bugs inside the main. We call that the manifest bug inside the main there. And we write that in the theorem, summarize the result in the theorem. So you don't need to understand it. You can look into the paper. So we have a triple. I just explained fusion behind the triple precondition P in the blue color and the post condition Q. So we just say that if we don't have any condition, any in the precondition, and in the post condition, we must sure that this is not the unsat, not the net code. So we report, we classify it as the manifest bug. And next we talk about the implementation and experience evaluation. So just ask about the scientists and real work. Scientists seek for perfection, and real work actually that idealities. So how we get a compromise. So in the implementation, we had to choose to develop a very fast tool but dumb, or very slow but very smart, not report many point positive. And we choose because that's our in context of a company. So we choose the first one, fast but dumb, a little bit dumb, hopefully. Okay, so and we based on the substantive just support equality logic. And also in shortcut, there are lots of functions about pointer function and null functions. We don't know how to analyze. Don't have a triple for that. Okay, so our tool PoolS might produce point positives. Okay, that we choose the rule. And for evaluation, we evaluate our tool in OpenSSL and other 8 open source developed by Facebook. And how we classify a box. So a box, we call that a box if we can find some fix for the box. Developer, they fix the box. Or pending box if the fix we propose, but developer haven't fixed, haven't agreed. The last one, point positive, if we couldn't find a fix for the box. And our plan is that we run PoolS and infer on the project, collect timing and box to compare the performance and precision. And we're going to answer 3 research questions here. The first one, for on OpenSSL 1.1.1 hash, PoolS better, more precise than infer. And second, we choose that version of OpenSSL because in 2014, infer found 15 bugs in this version. So now we just want to return it. The second hypothesis is that PoolS find new bugs in OpenSSL for the current OpenSSL. The last one, the performance of PoolS is comparable to infer. So I'm not show the detail, but I have some backup slide at the end. Also, you can look into the paper. Now it's available online. So we confirm 3 research questions. So on average, fix rate of PoolS is around 61 and infer is around 23 to 59. And PoolS found 15 new bugs, and we propose the fix. And OpenSSL developers agree with us and accept our pull request. Except the last one, our performance, the tool is compatible as good as infer. And when we will develop our proposal inside the pools, that is the discipline of PoolS in Facebook, and deploy to the production process as Facebook, the fix rate is 82%. So I think that's quite good result, quite decent. That's the last one. So just for conclusion, we propose some direction in the bug finding tool under approximate biaction to positive theorem. And we also talk a bit about the experience. Our tool find 15 new bugs, and the fix rate is maybe 2.7 better than infer and as scale as infer. So we have some continue working on that direction, but I just want to focus on the second option. We talk about scalability and precision. So we very much want to working on a compositional for simple execution, version of simple execution for KLEE and or CPMC. Actually, I did some implementation, put some IL triple in KLEE and do the top down, but it's some technical difficulty because maybe I very much want to collaborate with people in KLEE, in the KLEE team, and we can work together to solve this problem. I think it's quite interesting problem and must KLEE scale and can deploy in CI environment. So thank you very much for listening.